sand is blowing up the dune, if you can get your eyeball down there and look at it without getting your eye full of sand, you would see that the sand grains don't roll up the sand dune, they don't slide up the sand dune, but they jump, they bounce up the sand dune. All of those are called saltatory movement. So this is saltatory conduction. It jumps from spot to spot. All right, let me see, we down those wrinkle like All right, let's do one more concept here, Tiffany.
So is like those scribbles, like in groups, is that myelin?
That's myelin, right.
And that causes it to jump?
Yeah, because the ions can't get through the myelin sheath, so the only places they can get through are at the nodes. And so that's where the flipping takes place, and that's why it goes faster. And that, by the way, is why with MS, multiple sclerosis, when the myelin is gone, then this flipping can occur all along the neuron, which slows it way down. Yeah.
Is it possible for a cell to function without myelin?
Well, it can probably function, but so slowly that it doesn't do any good. It doesn't
So
do any good.
unmyelinated is not normal.
It's not normal for our axons. There are some places in our body where we have unmyelinated sheaths, or unmyelinated neurons. But axons are generally myelinated. All right, for the last concept, I'm going to need a picture. Relative and absolute refractory periods are an important concept, and I know everybody gets scared when you see graphs and stuff like that, but this one isn't so scary. What happens as this nerve impulse moves along, as the polarity flips from -70 to +30, there is a short period of time when that part of the neuron cannot be stimulated again. How could it be? If the polarity already flipped, how can you flip it again? You can't flip it again until the ions get sorted out again, right? It's like flushing a toilet. Once you've flushed it and all the water is drained out of the tank, you can flip the handle all you want, but you're not going to flush the toilet again until the tank gets filled up again. And so it's kind of the same way here. If all of these sodium ions have rushed in, you can't cause them to rush in again. They already rushed in. So even though that sodium gate is only open for 1 millisecond, once it closes, you can't flip the polarity until you start resorting out some of these ions again. Make sense? You got to restore some of the original polarity before you can flip the polarity again. Hopefully that makes sense. So during a short period of time, I actually think this graph is wrong. You have to watch out what you get off the internet, but you can look up the numbers yourself. According to this one, in the first 1 millisecond, it's impossible to flip the polarity once again. And I think the book actually gives a different number. We'll have to look that up. So I think it's the one you want is on page 398. That's just a little bit over 1. It's in the absolute refractory period. Okay, so that means that our voltage or membrane potential is way up here in the plus something, plus 30 range, and you absolutely can't flip it. That means that for that 1 or 1.2 milliseconds, that neuron cannot fire again. All right? That make sense? Okay. It's just like you can't flush that toilet again. But as the ions start to resort themselves out again, so that we start to restore our resting membrane potential of -70. As we do, once we get it all the way back to -70, we can fire that neuron again. Okay, so there's the two extremes. Over here, we can't fire at all. Over here, it can fire normally. But what about in between? Well, there is a period of time here where a really strong stimulus over here can cause the polarity to flip again, even though it wasn't totally restored. It's largely restored, but it's not totally restored. It looks like it starts at about negative, I don't know what that is, 40 some. It starts to be restored to the point where you could flip that polarity again, but it would take a really strong local potential to get it to happen. All right, so, and now here's the key to answering Liz's question. There'll be two things, by the way. Number one, this isn't Liz's question, this is something else. This keeps the nerve impulse going in one direction. This is why neurons are a one-way street. Take a look up here. Let's say that we've got our polarity flipping right here. Here's where the action potential is, right here. In order for it to go back that way, it would have to reflip this one. But this one is still in the absolute refractory period. This one might not be, but this one is. And therefore, you can't send the impulse back that way because the area right next to where the nerve impulse is, that is still always in the absolute refractory period. And so you can't flip that one again. And so the only one that will flip is this. And so it'll continue this way, but it can never go backwards. Does that make sense? Mm-hmm. Okay. Now to Liz's question. Make sure you're done writing what you're writing, because you got to really pay attention to this one. A normal impulse, a normal sound, whatever that is, a normal feeling, a normal smell, who knows what normal is, but let's just say there's a normal, could happen, according to this diagram, if it's correct, could happen about every 4.5 milliseconds. Does everybody see that? Here it happened, and then it absolutely can't happen there again. And a normal one could happen when we get things fully restored, which is at about 4.5 milliseconds. Everybody got that? Okay. So a normal stimulus, whatever that is, could happen every 4.5 seconds. Or milliseconds. But we did say that in this time period, we could get another impulse if the local potential were really strong. So if you get a stronger stimulus, a louder noise, it could maybe trigger it here, right? And so now you could have an impulse every 3.9 milliseconds. If the noise was louder yet, it could trigger it back here. And you could get one every 2.5 milliseconds. And if it were really, really loud, you could get it triggering it way back here, just out of the absolute refractory period, every 1.5 milliseconds. And so when you finally are aware of how loud the noise was, it's not due to how many of these gates open. They're always, or how long they stay open. The same number always open. They always stay open with 1 millisecond. It's not due to that. It's due to how many times per second this neuron can fire. So big stimuli can get this neuron to fire many, many times per second. smaller stimuli only get it to fire fewer times per second. And the very, very smallest of the stimuli will only get it to fire once every, what was it, 4.5 milliseconds. All right, so, so your brain interprets the magnitude of the stimulus by how many times it's receiving that impulse per second. So when I just barely touch the surface here, I'm probably getting that stimulus once every 4.5 milliseconds to my brain. If I smash it with a hammer, I'm getting lots and lots and lots of them per millisecond, because it's throbbing and it's refiring at it. Just as soon as it's out of the absolute refractory period, it's firing again, because it was a huge local stimulus over here. All right, that's probably enough to digest.